Hello and welcome to this brief presentation on cybersecurity and the Enhanced Security Module. With the coming wave of autonomous vehicles, a safe vehicle must also be a secure vehicle. You can't really have one without having the other. And now, as components become more sort of interwoven and connected, this focus becomes more and more important. So traditionally, we had a sort of self-contained component here where you'd have an application running on a single piece of hardware, and then you could draw a threat boundary just around that component. So you could trust whatever was running inside the component. Nowadays, we have a much more complicated system where we'll have multiple components connected to each other, and SAFERTOS running with other software from sort of third party potentially. And with this case, we have to draw a threat boundary inside the component itself. So now we have added in an additional enhanced security module. This now controls the application's access of SAFERTOS. So we can kind of reinforce the security of the kernel and make sure that any access to the SAFERTOS itself is controlled. So briefly, this is a kind of a rundown of the features of the ESM. One thing to note is that it's being developed in accordance to ISO 21434, which is the cybersecurity standard for automotive. So firstly, this first feature we're going to talk about is the access control policy. You might have heard of it called an access control list, and essentially what it does, it controls the task access to the API. So in this case, just as a very simple example, we have two tasks which are either sending or receiving from a queue and then checking the number of messages that are waiting on that queue. Usually a SAFERTOS application designer could say, right, I'm going to make these two tasks and they're going to use just these two functions, and there won't be a problem of having access to any other functions because you're in control of kind of the API functions that it's using. However, with a bad actor, having access to the whole API means that they will use API functions that are outside the scope of these two tasks. So they could maybe delete a task or delete a queue or enter a critical section, do things that are beyond their scope. So with the ACP, we can now very finely limit a task to the APIs that it must have access to. This also carries for interrupt service routines as well. So we can ensure that all interrupt service routines running in the system can only use, in this case, queue send or queue receive from ISR. This follows on to also restricting the objects a task has access to, or as we call it, a OACP. So task A can only use queue send or queue messages waiting, but we can also restrict on what object task A can call those functions on. So if task A tried to receive or tried to send to Q2, it has permission to use this function, but it doesn't have permission to use this object. And so once again, we're like further restricting the scope of the task's sort of access within the system. This is a new kind of feature with the ESM as well, to do with obfuscating an object handle. Traditionally, an object's handle, which is how you would refer to an object in like a queue or a task or whatever, would point to the task control block or object control buffer, the area of memory that sort of controlled the configuration settings. Again, in normal SAFERTOS, when we're not considering security, that's fine because the kernel is the one that controls how the task or queue settings are changed. But in security, having this sort of indirect access to the object memory means that they can tamper with it without having to go through the kernel. So the ESM introduces handle obfuscation, where when you create an object, in this case a queue, the SAFERTOS keeps a private reference of the memory being used and will just simply return a random number or cryptographic hash or something, so that the application can only use a random number to refer to a queue. Following on from this handle obfuscation, we can also therefore separate application memory from kernel memory, because it no longer needs a reference to the kernel memory where, let's say, a queue is stored. We can make sure have application memory completely separate from kernel memory. And then we sort of usually use this using an MPU or some other memory protection unit. And in this way, we can even further separate where's the application space and where's the kernel space. We introduced a new model, which is to use hardware exceptions to automatically raise the privilege of the system, not the task. Then the kernel function executes, and on return, the privilege is automatically lowered again when the task is resumed. So this prevents this elevation of privilege. Lastly, the last feature I'm going to talk about is penetration detection. When you call an API function, you have a unique ID to say which function was called and what the result was. So in this case, we can see a task called an enter critical function, but it was denied access. And with these two sort of parameters, we can very narrowly decide, okay, an error has been returned, what should we do? Task enter critical is quite a serious function. It has quite big ramifications for the system. So in this case, we could, as an example, delete the task that called the function which didn't have access. Another example is, let's say a task wants to gain access to a queue. It doesn't know the handle, so it can just randomly pass a random number until it gets a successful result. If we keep account of how many times a invalid queue handle's passed, we can then say, oh, someone's trying to scan, brute force their way into a queue handle. So what we could then do is then remove the access to the queue function that it was using, in this case, queue send. So I've talked a lot about the ESM. There are some requirements that must be sort of met to run the ESM on your platform. The first one is at least 2 privilege levels. We have to be able to create that separation between application space and kernel space. The next one is a protected memory system. That follows on, it's the same sort of logic there. We also need a secure boot process. This is to ensure that when you load SAFERTOS onto a processor, we can guarantee that what's loaded on is indeed the intended sort of binary. Similarly, we need to make sure that flash and the vector table is immutable. We have to make sure that all the code being executed is what was initially loaded during that secure boot. And lastly, we have a means to secure outside communication. So we want to make sure that any processes, external components that are communicating with SAFERTOS or the host processor that SAFERTOS is on have access to communicate with SAFERTOS, and it's not being fed some rogue data. So that's the end of my presentation. If you have any questions, please feel free to ask them now. Thank you very much.